Good morning. We move on. We did operations last time. Now I want to look at how we can transform a function. And so the idea is we're going to have toolkit functions, what they're called. We know they're graphs, and we can use those graphs to sketch a transformation. Three broad categories of transformations. The first is a translation. So if you're given function f of x, the function f of x plus k, where k is a constant, is a vertical shift or a vertical translation of the function f of x. Notice this is saying all of your output values are being changed by k units. If k is positive, it is an upward shift by k units. If k is negative, it is a downward shift by absolute value of k units. Function f of x minus h is a horizontal shift or a horizontal translation. Notice here, your input values are changing by h units. If h is positive, the graph will shift to the right by h units. If h is negative, it will shift to the left by absolute value of h units. Notice the slight difference. Plus, minus. Generally speaking, any horizontal transformation is the opposite of what you would expect. Right? If this was f of x plus 5, it wouldn't shift to the right. It shifts to the left by 5 units. Second category of transformations are reflections. Again, consider a function f of x. Function negative f of x is a vertical reflection or a reflection about the x-axis. Again, notice your output values are being multiplied by -1. So they change sign. F of negative x is a horizontal reflection or a reflection about the y-axis. In this case, all of your input values are being multiplied by -1. Then the third category, stretching or compressing. So the function f of x, new function a times f of x, where a is a positive constant, is a vertical stretch or vertical compression. Or you may hear vertical shrink. If a is greater than 1, it is a stretch. Specifically, f is being stretched by a factor of a. If a is less than 1, it is a compression. It is being compressed by a factor of 1 over a. This is where there's a typo in the book. But your book keeps it as being compressed by a factor of a, which is incorrect. Function f of bx, where b again is a positive constant, is a horizontal stretch or compression. Just like with translation, the horizontal works in the opposite way of what you would think. If b is larger than 1, the graph is being compressed by a factor of b. B is less than 1, then it's being stretched by a factor of 1 over b. Two undervalued properties. Even and odd. Before we get into it, when you hear even, what do you generally think?
Are they the same? The same, even is something that is the same.
What do you mean by the same? So it's what, a multiple of 2?
Or just anything that can be split evenly? Or everything that leaves the same?
What do you mean split evenly?
Like you have 2, you have 1, 1, and 20, you have 10, 10. Or like you can do...
When you say 10, 10.
Like in half, evenly?
Do you mean 10 plus 10 or 10 times 10?
Like 10 plus 10.
Yeah, so a multiple of 2.
Yeah.
2 times a number. And then odd, you typically think of even plus 1. Like 2 times the number plus 1. 1, 3, 5, 7, 9. And then 2 is the only even prime number. Every integer has to be even or odd, correct? And there's no integer that is neither. Yeah, functions have no similarities to that. Say a function is even if f of x equals f of negative x. Function, graph of even functions, symmetric about the y-axis. Which means if you take an even function reflected about the y-axis, it's the exact same. Function is odd if f of negative x equals negative f of x. Odd functions are symmetric about the origin. So you reflect the graph of an odd function through the origin, it's the same. Typically, you look at symmetry. You look at x-axis, y-axis. Origin's also pretty common. Those are not the only types of symmetry, of course. You can have symmetry across any line. So even something as simple as x squared plus 1. That is not symmetric about the y-axis, but it still has symmetry. No, I'm sorry. X squared plus 1 is still symmetric about the y-axis. X plus 1 quantity squared. Do one of these two conditions, no, this is negative f of negative, same thing, negative f of x is f of negative. Does every function satisfy one of those two conditions? Does? What about x cubed plus 1? Does it satisfy one of these? So x cubed plus 1, if you take f of negative x, is that the same as f of x? If you take f of negative x, is that negative f of x? Functions can be neither even nor odd. And generally speaking, the vast majority of functions are neither. But the functions that satisfy one of these two, it's a useful property to know. Specifically, let me get the trig. Next up, we take a look at the toolkit functions. Right, so these are functions whose graphs you might want to remember. We have the constant function. f of x equals c for some arbitrary c. Right, it has domain of all real numbers. Its range. Do not know why it's written that way. So that's not how range would be written for a single value. Sadly, it doesn't look like I'm actually going to correct that because that's a pasted image. Constant function, generally pretty boring. Even the next function is boring. Identity function, or your linear function. F of x equals x. So we're going to stick with the identity, because linear can be anything mx plus b. Oh, wait. Wrong slides are changing. That's better. It's the diagonal line through the origin. Slope 1. Domain all real numbers, range all real numbers. Of course, you can notice just by looking at that, identity function is odd. And it's symmetric through the origin. Absolute value function. Domain all real numbers. Range non-negative real numbers. Absolute value function is even. You should be able to see that. Folded across the y-axis. Same thing. The two sides line up. Your quadratic function, x squared. Domain all real numbers, range non-negative real numbers. Again, quadratic is even. Cubic. Domain and range all real numbers. This is symmetric about the origin. It's odd. Reciprocal function, 1 over x. Domain and range, everything except 0. Symmetric about the origin. It's odd. Reciprocal squared function, 1 over x squared. Domain, everything but 0. Range, positive real numbers. And it is even. It is symmetric about the y-axis. Actually, this kind of function occurs a lot. So much, in fact, in physics we call it an inverse square relation. First one that pops in my mind is gravity. Gravity is an inverse square relation. Force equals gmm over r squared. Square root function. Domain and range, non-negative real numbers. Is this the last one? I think the one coming up is the last one. Yes. And the cube root function. Domain and range, all real numbers. Notice square root, if I go back, has no symmetry. Cube root does. And cube root is symmetric about the origin.
So that would be odd.
So of the toolkit functions, only the square root didn't have symmetry. Wasn't even nor odd. The others were one or the other. The constant function, by the way, is even. And fairly obvious. Now the cube root function is also pretty interesting. Because of this point right here.
So 0.
Absolute value, you'll learn this one in calculus, doesn't have a derivative at that point. But that's because the tangent line is actually infinite. Has infinite slope. All right, so generally whenever something meets at a point, there's no derivative. There's no derivative here either. For a totally different reason. Here, the tangent line just doesn't exist. You know, leave that for the study of calculus. Now here's the question. do have it saved. So what we're going to be doing for the rest of today is sketching graphs. This is where you're obviously going to have an advantage if you have graph paper. Sadly, I don't have that option, but that's okay. Because I have a little tool called Mathematica that I can use to create myself a coordinate system. So this way I don't have to worry about sketching out the coordinate system and making sure all the ticks are nice and evenly spaced. We want the absolute value of x minus 1. We're going to start by describing the transformation. What's the toolkit function we're using?
Absolute value.
The absolute value function. That's the first thing you always want to identify is what is the toolkit function? Now, look at it. What transformations are being applied?
Horizontal. Or vertical.
So it is a vertical translation.
Going down.
By how many?
1, negative 1. Or going down 1.
Are there any others? No. So this is just the absolute value function translated downwards by 1 unit. What I would do is I would draw both graphs just to compare them. No, dear. Okay, so this is definitely not drawn to scale. That's not good. Why is this scaling off so much? That's not what I want. Let me... maybe try not changing the size, see if that affected the scaling. It shouldn't have, because I thought I changed both horizontal and vertical the same. So that shouldn't have affected anything. This should be a 45. No, it's not. Oh dear, the scaling is definitely off. Oh, Mathematica, why do you do this to me? Let's That's what I thought. So adjusting that size definitely didn't affect anything. Right, because it should, on both sides, go through each of these corners. Right, that should be a 45-degree angle on both sides with respect to the y-axis. But the scaling is off for some reason, so it's not. And that is actually very aggravating. So I'll do the best that I can. Oh, that was terrible. Oh, that's lovely, but whatever. Say it's good enough for government work. That is the absolute value function. Absolute value of x minus 1, it's going to look the same. It's just every point gets shifted down by 1 unit. So the easiest way to do that is look for the most convenient point, the vertex. Shift the vertex down 1 unit, and then the shape is identical. So something like that. Absolute value of x minus 2. Again, you first want to identify your toolkit function, which they actually do give you. Then identify the transformations that occur. So what's the transformation?
Horizontal
How?
to where is it?
Yeah.
To the right.
By what?
To
And again, convenient point to pick. The vertex that goes to the right 2 units. Good enough government work. And that shape's the same. So also what I'm going to do is come back to here. What's the domain of the new function? What's the range?
All our number is greater than -1.
Just greater than? That's for the absolute value function. Notice what changed and how it changed.
System.
So what do you mean by the same?
All our numbers. And then the range is the same as well.
Did the domain change? Technically, yes. It just doesn't show. We shifted 2 units to the right, which means what we did to the input values was take 2 units away from every single input value, which means both of your endpoints actually shifted as well, 2 units to the right. So it's -infinity plus 2 to infinity plus 2, which is still everything. And I used that very lightly, by the way. -infinity plus 2 technically is undefined. -infinity is not a number, which is why you can't say infinity minus infinity is 0, because it's not. It's actually a really good YouTube video by Vsauce on infinity.
I think I heard him.
Vsauce is good.
Yeah, I've heard him.
His infinity video is one of my favorites. Okay. Identify the toolkit function. and then identify the transformations on it.
Just going to the left 2 and then 1.
Write it downward this time. Same thing. It doesn't matter which happens first. All right, so typically we just read it from left to right. So take the vertex, shift it to the left 2 units, and then down 1 unit. What's the domain?
All real numbers,
What's the range?
including -1, 30.
And again, just notice how domain and range are being affected. Identify the toolkit, then identify the transformations.
Is it a vertical reflection?
You tell me, is it?
I think so.
Yes.
How confident are you?
Pretty confident.
You're in Vegas.
Oh, I'm not betting on this. But
Except it's not money you're betting, it's points on your grade. All right, so 0 to 100. How much you betting?
30.
30. You can still pass if you're wrong. It's a shame. Could have guaranteed yourself an A.
That's
All right, vertical translation or about the x-axis. What else?
still up 3. No, I mean up 3.
Is that it?
No.
It's a vertical.
Vertical.
Reflection.
So we handled the reflection already. That's there.
Vertical shift.
That's the 3 units upward, isn't it?
That's not it.
It has to do with the two.
Mm-hmm.
It's a vertical. Compression.
By a factor of 2. When dealing with transformations, there is technically an order, a quote-unquote order of operations. Reflections are first, stretch compress is second, translations are third. It's technically how you're supposed to do it. It's not really how I look at it. I just go, oh, look, I'm moving 3 units upwards. So my vertex is going to be there. Then I know, oh, flips upside down. So I'll just draw it upside down.
Then would you have to redraw it with the vertical stretch?
Well, I'm going to have to now. Not redrawn, though. Now I have to deal with that stretch, and that is a pain. Every output value gets doubled. Then you add 3 to it. Right, so 1 would get doubled to 2, but remember it's going upside down, so it's -2. Then you have to add 3 to it.
One.
So it's going to have to go through there. Oh, and by the way, it also means it's going to have to go through there, because -1 is going to do the same thing. 2, -4, and then add 3. And so looking at the grid lines, instead of going through every corner, it goes through every other corner. Right. Essentially, the slope of each line got doubled. Right, so it becomes steeper. So if you actually visualize, right, you have, let's say you have some stretchy object that's originally in this shape. You pick it and you stretch it vertically. Doesn't that get thinner? So that kind of makes sense. What would be happening? Good enough for government work. Why is it doing ink to shape? It shouldn't be. Not like that. I'm going to start over. So something like that. What's the domain? What's the range?
Including 3 to negative infinity.
You said that backwards.
Negative infinity to including 3. But how would that, like, would that really matter?
Yes. When you do intervals, it's always lower bound to upper bound.
Well,
3 is your larger bound. And this is where the order matters. And so domain didn't change. Range did. The first thing we did with the range was multiply by minus. So it flipped from 0 to infinity to negative infinity to 0. Then all of the output values got doubled. Well, twice of a negative infinitely large number is still negative infinitely large. Twice of 0 is still 0. So that's why it doesn't look like that caused any kind of a change. Then all of your output values had 3 added to it. Negative infinity plus 3, still negative infinity. And then 0 plus 3 is 3. Identify the toolkit. They told us. Now identify transformations.
that can be reflected about the y-axis.
And that's it, right? So square root sketch that graph. Obviously start at 0, pass through there. 2. There. Let's not draw there. There. So there's the original function. And since this is just a simple reflection, It's going to look the same, just drawn the other way. Which is where the tough part comes in. Oh no. Whatever. It's good enough for government work. Yeah.
When would it reflect into the negatives?
Is that when it's outside of the cubic root?
Yeah, be when it's outside.
Or no?
There's a domain and range, right? What's the domain of the new function?
Opposite,
Which would be what?
when everything is negative zero, negative infinity to everything equal to 0.
What about the range?
Opposite.
So what's the new range?
Segment from 0 to
Everything
So not negative infinity to 0.
positive. It's positive
is
is
not going down anymore.
So what is the range?
Is it 0 from infinity to 0 to infinity?
0 to infinity, that didn't change. Right, all we're doing is affecting the inputs, so only the domain will get affected. Oh, oops. What the? Identify the toolkit. Now identify the transformations.
You reflected over the x-axis.
5, negative 3.
You compress it by 3.
What kind of compress?
Vertical.
I do agree, it's definitely a vertical.
So it's a stretch.
Mhm.
But if it's less than 1, would it be a compression?
Is it less than 1?
Is it just a 3, not a negative 3?
Right, so notice the restriction on A for the vertical stretch and compression. What did we say A had to be?
Oh, A to the negative 1.
A had to be greater than 0. So if you have a negative constant out in front, it's 2. The negative it's a reflection, then you just look at the absolute value. So you ignore the -3, it's just 3 that you're looking at. So first reflect it over the x-axis and then stretch it vertically by a factor of 3. 2 was bad enough, 3 is going to be even worse. Now 0 doesn't change. Square root of 1 is 1, but that gets tripled. Right, so every output value is essentially getting tripled. And then negative. And I'm already, I think, out of room. Oh, no, I'm not. 34 would be 2, but it gets tripled. Down to 6. And I can't do 9. Can I? Yeah, I can, because that'd be 9, right? 6, 7, 8, 9 would normally be 3. Gets tripled. 9 right there. Would have been a lot of trouble if it was 4. Maybe something like that. What's the new domain?
0,
Same thing, right? We're not affecting the input at all. What's the new range?
-0.
Right, there are technically 2 effects on the output. Negative and then tripled. But triple of negative infinity is still negative infinity, and triple of 0 is still 0. So that's why it only looks like there was 1 effect. Why is that going down there now? I don't get it. Because that got adjusted, that's why. So what I have to do then is identify the toolkit, identify the transformations.
Can that be a vertical shift of 3 or no?
What?
Stretch on
Kind of stretch.
horizontal stretch. Then vertical stretch. One more.
So then it wouldn't technically be a stretch. Because we're compressing it. So if you stretch it by 1/2, it's the same thing as shrinking it by 2. Because they're opposites.
So if it was 1/4, you'd be compressing it
By 4. That's why I said what the book has is wrong. Because they do have it as they would say shrink by a factor of 1/2, which makes no sense. What else?
To the left.
So I don't have to change colors. Multiple times. Domain. Going to be there. And now, the compression. This is going to be annoying. All right, so square root of 1 is 1. That's going to move to the left by 3. And multiply by 1/2. I don't know, right there. All right, so then square root of 4 is 2. That gets moved over to the left by 3. And then cut in half. This should be 9. It's 3. Move over 3. And then cut in half. The next perfect square would be 16, which if we moved over by 3 would be 13, which isn't on our graph. So those are really the only 3 convenient points, 4 convenient points we have to work with. This is terrible. What's more is I have to make it look like it's still increasing with a downward curl. What's the domain?
-3 included on infinity.
Right, all of your input values just get shifted 3 units to the left. And what's the range?
0 included on infinity.
Right, all of your output values get cut in half. Half of 0 is still 0. Half of an infinitely large number is still infinitely large. This one. Toolkit is still square root of x, so identify the toolkit, identify transformations.
I mean, horizontal, stretch, compression,
Horizontal.
vertical compression, 25.
You want any of them?
Hmm?
You want any of them?
Yeah, doesn't matter.
Up to.
To the right,
Reflect over one. And then vertical stretch.
There's 1.5 and 1.5 is a half, like last number. So you're just adding one.
I do not agree with y-axis.
It's not long.
Your output values switch signs, which means you go over the x.
Makes no sense.
Right, vertical reflection. It reflects in the vertical direction, which means over the x-axis.
Yeah.
Right, again, that's kind of weird because you always think anything x would be horizontal, but with reflection, it's how is it reflecting.
Yeah.
Wait, so there's no vertical or horizontal?
There is a stretch or compression. What kind?
Stretch.
Not vertical stretch.
I do agree vertical, and I do agree stretch. By what?
So 1.5.
Stretching by a factor of 1.5. Lovely. That should be our new vertex. 2 units up, 1 to the right. We'll be upside down. Now we have to deal with that stretching. Every output value gets multiplied by 1.5. So 1. So I have to do the opposites because it's going upside down. I have to do the opposite with the vertical. So I go 1 to the right. No, that's not right. Is it right? Oh, yeah. 2 down. and multiply by 1.5.
Oh, you would have like one of these on like the test or quiz.
Could be. Or you just have to sketch the graph. I'm just going to do it this way. So when x is 2, becomes the square root of 1, which is 1, times negative 1.5, negative 1.5, and then up by 2. Right there. Next perfect square is 4, which occurs when x is 5. 2, 3, 4, 5. It's 2 multiplied by negative 1.5. So it's 2 times 1.5. 3. So it'd be negative 3. That kind of looks right. Oh, and then plus 2. So we'll be at negative 1. Next perfect square is 9, which happens at x equals 10. All right, 3 times 1.5 be 4.5, so it's negative 4.5. 4.5, and then add 2, 1, 2. So it'd be like right there.
As long like say like we were supposed to like draw a graph like on a test or quiz like this, as long as we have like valid points on the graph, like would that be cool? Like if I did like
As long as it looks similar to what, because I'm not sketching the graph in the solution key, I just print out the graph. As long as it looks close to that, you're good. Like it has to cross axes at the right place, or close to it in this case, because you don't have an actual.
so you wouldn't really be looking for like the exact points, or would you?
If you want to put the exact points, go ahead. So I'm going to make sure it comes close to those points. Right, so if you drew this instead, something like that, you would lose points. Because that's definitely way off of what it should be. Right, so it's got to be relatively close. Huh? Why am I missing? Oh dear. Oh dear. Excuse me for a minute. I'm missing some questions and I don't know why. Ew. Guess what? No. Deal with that. Yeah, I don't know why these weren't there. Oh well. Problem solved. And now we're going to determine whether a function is even, odd, or neither algebraically. And so what we want, oops, not f of x, sorry. So evaluate f of negative x. Now, because for both even and odd, that's what we have. F of negative x equals something.
So realistically, all you really gotta look at is like if it's like flip over the y-axis or.
Well, that's if you have a graph. That's not a graph. You could graph it, but determine it algebraically. Because I believe I did specify that you had to do it algebraically. Absolute value of negative x is what?
Thanks.
However, I want to keep it like that. Because I don't know if x is positive or negative. But I do know the absolute value of negative 1 is 1. So that becomes just absolute value of x. Negative x to the 10th power. X to the 10th, right? Negative 1 to the 10th power is positive 1. Oh, and then plus 5 doesn't change. So look at that. Is that f of x? Oh, I forgot something. Got that plus 12. Decided I didn't like 12 today. Is that the same as f of x? Yeah, that is f of x. That's the definition of even.
So it's even because it's the same f of x.
F of negative x equals f of x.
Okay.
Here's another way you could look at it. All right, this would be more of a logical. Absolute value is even. X to the 10th is even. 5 is even. Even plus even plus even is even.
Is it 5 odd?
Talking about functions. 5 is even in terms of function because it's a constant. So you have the sum of 3 even functions, which is even. So the result has to be even. Right. That's more of a logical look at it.
Yeah.
M of negative x. Negative x to the 5th power. What's negative 1 to the 5th?
I don't get why, like, you're doing negative x when the original one is m of x.
Even and odd both deals with m of negative x. Right, if you look back at the definition. Where is it? Right, so evaluate the function at negative x and see if it satisfies one of those two. Negative 1 to the 5th. Negative 1 cubed.
Negative 1.
There's a negative factor in common. Factor out the negative. Is that f of x? No. Or not f, sorry. Is that m of x? No. Is that negative m of x?
Yes.
Yes. What's in parentheses? Isn't that m of x?
Oh, it's because you factored out the negative.
Even if I didn't factor out the negative, it's still negative m of x. Because every single term had the sign change.
Yeah.
I just wrote it with the negative factored out to make it more explicit.
Yeah.
That's the definition of odd. And again, you can look at this logically. X to the 5th is odd, x cubed is odd, x is odd. Constant times an odd function is still odd. So you have odd, which is odd. What do you think even plus odd would be?
Even.
It'd be neither.
Yeah.
There's no consistency.
So it has to be strictly all evens or strictly all odds when you add or take the difference. Multiplication and division works a little differently though. Oh, this one's cool. Again, just start with r of negative x, see what happens. Can I really do anything else with that? Is that r of x? Is that the original function? Is that r of, or is that negative r of x? How do I want to write it? I'll write it that way. It does not equal r of x or negative r of x, right? It doesn't equal either one. Which means r of x is neither even nor odd.
Why do you put the 3 dots?
That is shorthand for therefore. Right, so I did the work.
Yes.
So this is my work. Therefore, I'm concluding this based off the work.
Okay.
So z of negative x. Negative 1 squared. Is that z of x? So what can we say about z of x?
Even.
So z of x is even.
So since this one is short, I'm still not getting like I feel like on like a test or thing, I would like be able to substitute the negative x in and then like make the actual equation, but like how do you like know if that's even? Like
Because when you simplified it, didn't you get the exact same function?
so if anything else was different, like say it was like 49 plus like x squared would be odd.
So it wouldn't be even in that case. To be odd, your result would have to be negative square root of 49 minus x squared. That would be odd. So if you can't get either one, it's neither. Oh, this one's a joke.
Is neither?
Is that g of x? Is that negative g of x? What's the conclusion? This one's odd.
Is there a reason we have to know this? Like it's gonna follow up something else, or that's
Very useful with trig.
okay?
But again, you're asking a math person if there's any reason you need to know this, and the math answer is who cares? It's interesting. So we study it. We math people don't care if it's useful or not. It's there, it looks pretty, so we study it. But yeah, we will be using it. Look at f of negative x. Negative 1 cubed. Negative x cubed in the numerator. Divided by 2 times can factor out a negative and write that as x plus 1, right? I can continue to simplify. Negative 1 cubed, negative. Negative over negative is positive. That is what we would get. Is that f of x?
No.
Is that negative f of x?
No. What's needed?
All right, so it doesn't equal either f of x or. So the conclusion is.
So wait, can you show me how it would look if it was negative?
Look at f of x. The definition for f of x. Put a negative out in front.
So it would be it's like negative and then.
Yeah. So multiply essentially just one of those terms by a negative. And that would be negative f of x. All right, much like what happened here.
It's just like
right, wound up being a negative because every term flipped sign.
Okay.
Right here, because it's division, it works a little bit differently. You'd only want the numerator or denominator to change sign. Right, even if the numerator didn't change sign, because of how the denominator looks, you still wouldn't be able to get negative f of x. So it would still be neither.
Would it be even if everything's negative? It would just be positive.
So let's say this was x squared instead.
Yeah.
This would stay as x squared, right? That negative wouldn't be there. I'd still have a negative here, but notice that's x plus 1 now.
Yeah.
Not x minus 1.
Oh, okay.
So that's still not negative f of x.
Okay.
So it's still neither be even nor odd.
Yeah. Okay.
So your first quiz goes up on Monday. All right, and again, I'll discuss that on Monday. Continue working on the project. That looks like it's coming due next Wednesday. And then, of course, you have 2 homeworks to be working on. Have a good weekend.